Greetings, Mr. Sutton here, bringing you the Pre-Cal Honors 9.5 Extra Practice Number 3 solutions on limits at infinity. To find this limit to infinity, we start by taking the slower growing terms and basically ignoring them. So choose your champion kind of thing. In the numerator, all we have to think about is the x squared. And in the denominator, the fastest growing function there is the 3x squared. So that's all we're going to look at here. At this point, we can cancel out these x squareds. So that's just 1 over 3, and that is our limit. On this problem, we're trying to find the limit as x approaches infinity of negative x factorial over x to the x. So for this one, there's only one thing in the numerator and denominator already, so we don't have to ignore any slower growing terms. What we have to do at this point is figure out who's growing faster, the top or the bottom. X factorial is pretty fast, but the only thing faster is x to the x. So x to the x wins in this one. This is a bottom-heavy function, which means that my fraction, as my denominator grows bigger and bigger and bigger relative to the numerator, my fraction keeps getting smaller and smaller, approaching 0. On this one, to find the limit as x approaches negative infinity, we start by disregarding slower growing terms. So we're going to just forget about negative 2x and 3, because as we go to infinity, those become insignificant compared to the x squared. And now we'll just plug negative infinity into the x squared. So since I'm squaring a negative, that becomes a positive, but infinity times infinity is just more infinity, so positive infinity then. The key to doing this problem, taking this limit to negative infinity, is realizing that this cosine x over x term is a bottom-heavy function. So as we go to infinity or negative infinity, this term here, since it's bottom-heavy, is going to 0. So this is really just 0 minus 1, which is just negative 1. To evaluate this limit to negative infinity, we start by choosing a champion inside this cube root function. So this 3 we can disregard. That's slower growing than the 2x squared. This 2 down here we can also forget about. So we can rewrite this as the limit as x approaches negative infinity of cube root of 2x squared over 2x squared, which is awfully convenient because that's really just the cube root of 1. And the cube root of 1 is just 1. So that's our limit. For this problem, we're trying to figure out the limit of this expression as x approaches negative infinity. So we've got two different negatives in here. At this point, I'm actually just going to go ahead and plug in negative infinity. I mean, we've only got one x. We can handle 1 infinity, right? So I'm thinking about this as e to the negative 4 times negative infinity minus 1. So this is going to be e to the positive infinity then if I multiply these together. And e to the positive infinity versus negative 1, e to the positive infinity is growing much faster. So this whole term then is going to be dominated by the e to the infinity and grow to infinity. On this problem, trying to find the limit as x approaches infinity, I'm going to choose my champion on each side. So in the numerator, I'm only going to consider the square root of x squared. I can ignore this plus 2 in here. In the denominator, this plus 1 makes no difference as x goes to infinity, so we just have the x to worry about. And this is really, the square root of x squared is really just x, so we have x over x, which conveniently is just 1. For this problem, to take the limit to negative infinity, I'm going to ignore the slower growing term 16 in the denominator. So now we just have 16x over x squared. And since this is a bottom-heavy function, x squared grows faster than 16x, this is just going to go to 0. For this problem, to take the limit as x approaches negative infinity of this polynomial, we're going to start by disregarding slower growing terms. So I'm only going to consider this negative x to the 5th because everything else grows slower than that. And now I'm just going to go ahead and plug in negative infinity for x. So this is, let's see, negative infinity to the 5th power is just negative infinity again. It's an odd to it's a negative to an odd exponent. It becomes negative. And then if we have negative infinity with a negative out front, that switches to positive infinity. So that's our final limit for this one. For this problem, taking the limit as x approaches infinity, I'm going to ignore this minus 3 in the denominator. It grows more slowly than 4x squared. I mean, it actually doesn't grow at all because it's a constant. So we really just have negative x to the 4th over 4x squared. Still have that limit hanging around though. And now if I reduce this, this is negative x squared over 4. plugging infinity into this, we end up with basically infinity over 4, which is infinity, but we have this negative out in front. So overall, that's going to give us negative infinity for the limit. For this problem, we're having this function f of x defined as 3x plus 5 over x plus 2. We want to know which of these statements is true. So the first two statements talk about horizontal asymptotes as we go to the right and the left, both at 3. The third statement's talking about a vertical asymptote at x equals negative 2 because we have an infinite limit as we approach negative 2. Okay, so let's analyze these one at a time. First thing to note, since this is a rational function rather than an exponential function, that means the left and right asymptotic behavior is going to be the same for this one. So we can say that the limit as x approaches infinity and x approaches negative infinity are going to be the same. And to find that, we just have to ignore the slower growing terms in the original function. So choose your champion. In the numerator, we have 3x. Denominator is just x. 3x over x reduces to 3, so that means we do have a horizontal asymptote at y equals 3. So at the very least, 1 and 2 are both true. So anything that doesn't have both of those in it can be discarded, such as answers A and B. So really now it just comes down to whether or not this third statement's true. So we do have a vertical asymptote at x equals negative 2. Negative 2 zeroes out the denominator, and we can't cancel out the x plus 2. So this must be a vertical asymptote rather than a hole, rather than a removable discontinuity. So that means vertical asymptote must be at x equals negative 2. And as far as the reasoning goes, if there is a vertical asymptote, then this reasoning about approaching negative infinity as you go to negative 2 from the right side, well, that could be true. If we really wanted to verify it, we can pick a number a little bit bigger than negative 2 and plug it in. So let's say negative 1. Yeah, let's try negative 1.9. If I plug in negative 1.9, my numerator is going to be negative. My denominator is going to be positive. So overall, that'll be a negative result. So yes, that would imply that we're going to negative infinity. All right then, we're picking choice D. For this problem, we have population on an island modeled by this p of t function, and we want to know the limit as t approaches infinity of p of t. Well, I'm going to rewrite this a little bit here. So since we have a negative exponent, I'm going to call this term down here 30 over e to the positive 0.03t. And now if I take the limit of this expression, that means that this e term down here is going to infinity. So 30 over an infinity, that's going to 0. So I can write all of this as 5,000 over 20 plus 0. That's the limit as t approaches positive infinity. And 5,000 over 20, basically, what's that going to come out to? Well, that's going to be 250, so that's going to give us choice C.